Here we're going to talk about multiplicity. Looking at the molecule isopropyl chloride, what we see is a single hydrogen in the environment that's bound next to the chlorine. We also see 6 hydrogens in the environments that are bound out at the end, away from the chlorine, on the methyls. Because there's a plane of symmetry running straight down the molecule, these signals all end up in the same place, and so you get 6 hydrogens in environment B, a single signal for environment B. But what I'm interested in talking about here is multiplicity, which is to say how many hydrogens are near the signal in question. So if I'm looking at HB, what I really want to know is how many hydrogens are close to HB, close enough to influence HB. How close is close enough? 3 bonds. 1, 2, 3 bonds. HA to the carbon is 1 bond. Carbon is the second bond. HB to the carbon is the third bond. Likewise, because there's a plane of symmetry, you can see this. Going the other direction, there's a single bond between H and C, a second bond between the carbon, and a third bond between the carbon and HB. 3 bonds away is normal multiplicity. So A has 1, 2, 3, 4, 5, 6 neighbors. Meanwhile, B, all of the B's have A as a neighbor. What's interesting is that B's, because they're all in the same environment, don't usually serve as their own. B senses A and only A senses all of the B's. The rule of thumb for multiplicity is that any isolated hydrogen is going to have a single line. Said another way, if I have methyl chloride, I expect these hydrogens to all end up in the same place, so they are all HA. They have no neighbors 3 bonds away because they are their own neighbors, so they won't interfere with each other. And so what we expect that line to look like is a single line. We call this a singlet. What happens if we have one neighbor for a given line? The presence of any single neighbor causes the line to split into 2 new lines. We call that a doublet. What's interesting about this is that the line will end up split into 2 lines, and the relative intensity of the 2 lines is the same, 1 to 1. Now, what happens when we have 2 neighbors nearby? What happens when we have more than a single nearby neighbor? We'll get a little bit more complicated. For the molecule I've drawn now, we can imagine HA, all 3 of these hydrogens, to be in the same place. So we expect them to be a singlet. So A would be a singlet, isolated from everything else. Why do I say it's isolated? Because there's 1 bond between the HB and the carbon, 2 bonds, now counting HB to the carbon to the oxygen, a 3rd bond going from the oxygen to the carbon, and a 4th bond going to each of HA. 4 bonds is, generally speaking, too far to get a normal multiplicity relationship. If you look at signal C, which we expect to have 3 hydrogens in it, it would expect to have 2 neighbors because of B. So what would it look like? Well, it's going to be split into a triplet, and the middle part of the line should be twice as tall as the parts on the side, and the distance between each line in the signal should be exactly the same, and that distance is going to be determined by the influence that B has on C. We call this JBC. So the extent to which B influences C gives rise to a triplet with that pattern. C influences B, the 3 neighbors in C, leads to a 4-line pattern, otherwise known as a quartet. So HB we would expect to look like this. And here we have a 4-line pattern with height 1, 3, 3, 1, and the distances between any 2 lines should be the same. And we expect that distance specifically to be, again, governed by JBC. Why is that? Because whatever influence B has on C is going to be the same influence that C has on all of these are going to be JBC. Where do these patterns come from? That's what I'll show you now. If any one proton is isolated from its neighbors, then it always shows up as a singlet. The presence of 1 additional neighbor will cause a given proton to be a doublet with 2 lines, each of equal heights, 1 to 1. The presence of 1 neighbor turns a singlet into a doublet. The presence of an additional neighbor turns a doublet into a triplet. So 2 neighbors gives rise to a 3-line pattern with height 1, 2, 1. With 3 neighbors, you get 4 lines. 3 neighbors gives rise to 4 lines in the signal. You'll get a 1 to 3 to 3 to 1 pattern that we call a quartet. The presence of 4 neighbors gives rise to a 5-line pattern. 1 to 4 to 6 to 4 to 1, quintet. And these are the heights of the lines in the signal. This is an n+1 pattern where one neighbor gives rise to 2 lines, 2 neighbors gives rise to 3 lines, 3 neighbors gives rise to 4 lines, and so on. The heights of the lines are given by Pascal's triangle. We start with one height, and then the next one will be the sum of the next 2 lines of the line above. So 1, then 5, then 10, then 10, then 5, and then 1 again. That'll be a sextet. That implies 5 neighbors. 6 neighbors gives a septet. 1, 6, 15, 20, 15, 6, 1 as the relative heights, and so on down the line. So, presence of 7 neighbors is an octet, presence of 8 neighbors is a nonet, and so on. Pascal's triangle gives rise to the number of expected lines in a given signal.
The key rule for multiplicity is the m+1 rule. A single neighbor gives rise to a doublet, 2 neighbors gives rise to a triplet, 3 neighbors gives rise to a quartet, and so on down the line. You always have one more line in a signal than the number of neighbors. That is the m+1 rule.